We're now going to take a look at calculating volumes of solids of revolution. And the first methods that we're going to look at are called the disk and washer methods. Now it's interesting to note that using calculus, we can calculate the volume of certain types of solids. You're used to calculating area using calculus, like the area underneath the graph of a curve or the area bounded between two curves. But we can extend those techniques to actually calculate volumes for solids. And the technique that we use is really important because this technique is used in many other fields of science like physics and engineering to solve many types of problems. So take particular note the method that we use to come up with the formula. So first of all, let's go over what we mean by a solid of revolution. So we have down here a shaded region. It's bounded between two curves. Let's call the first curve y1 of x. And the second curve down here we can call y2 of x. And x is between a and b. So for x between a and b, we shade in the region between these two curves. Now what we're going to do is we're going to take this shaded region and revolve it around the x-axis, and as we revolve it, it will sweep out a solid of revolution. Now what that solid of revolution will look like is this. So here's what the solid would look like as we sweep the shaded region around the x-axis. So it looks sort of like a bell shape that has the top cut off and it has a hole running through the middle of it. And so what we want to do is we want to calculate the volume of this solid. So let's see how we're going to do that. So to calculate the volume of that solid, what we're going to do is take that shaded region and break it up into little rectangles like we have pictured down here. So we take the interval from A to B, and what we've done here is we've actually partitioned it into some subintervals. And then we drew little rectangles here that approximate the area of the shaded region between the two curves. Now let's call this first curve here y1 of x, and the second curve down here we're going to call y2 of x. And as we've said before, x varies between a and b. Now recall this result from calculus. Recall that if we take our interval from a to b and we break it up into n subintervals, each one being of width delta x. The delta x would be the width of the subintervals down here. So that's our delta x. That's this width right here. And that's equal to b minus a over n. Now recall from the fundamental theorem of calculus, this is actually part of the way the fundamental theorem is proven actually. If we look at the limit as n goes to infinity of the summation of f of xi times delta x, that's equal to our definite integral of f of x. So when you see something like this, you should realize that this part right here, the limit of the summation, that turns into an integral right here. The delta x becomes a dx. And what's inside here, the f of xi, any place you see like an xi, you just replace that with an x. So keep this result here in mind, and this comes from the proof of the fundamental theorem of calculus. Now to approximate that volume that we had seen earlier, we have these little rectangles, And we're going to sweep these little rectangles around the x-axis. And as we do that, they're going to form little washers. We know how to calculate the volume of washers. So we'll calculate the volume of them, and then we're going to sum all of them up like we have right here, and then take the limit as n goes to infinity to obtain our result. So if we look at, say, this rectangle right here, and we sweep it around the x-axis, it forms a washer that looks something like this. Alright, so that's our washer that we obtain by sweeping the second rectangle here around the x-axis. And now what we want to do is figure out how to evaluate the volume of that washer. Then once we know the volume for this washer, we'll be able to calculate the volume for all of the other ones and then sum them up. And then we'll take the limit as n goes to infinity to obtain our result. Now, this washer, what it looks like is this. Let's look at a side-on view of it. So that's something of what our washer will look like here, and it has a certain thickness to it as well. Notice that this distance right here that thickness right there for our washer is delta x. Now we want to calculate the area of the face of this washer and multiply by delta x, and that'll give us the volume. So now the area, let's notice here that we have an outer radius, call it R1, and an inner radius of the hole that we'll call R2. So the volume of this washer, we'll call it delta V, is going to be so you see what this is. This piece right here is the area of this shaded region right here. Okay, that's what this represents. It's the area of the outer circle minus the area of the inner circle. Now that represents an area. When we multiply by the thickness here, then we get a volume. So this is the volume for this washer down here. But now what we need to do is relate R1 and R2 to our given functions y1 and y2 over here. Well, the R1 is going to be this. I'm going to have to erase this over here. The R1 is going to be this distance. Okay, you see that distance right there is R1. Now, the relationship between R1 and Y1, if we label this point right here on the x-axis, say it's x sub I, where this denotes that it's coming from the ith subinterval. Okay, now this would be the second subinterval, but we'll just denote it as a general xi. Then the R1 is y1 of some xi. And the R2 would be the distance from here to here. Well, that's just going to be y2 of xi. And so we see that the volume of that washer that we had drawn over here is given by this. So that's the volume of that washer. And I should have little xi's right here. Now if we sweep each rectangle around the x-axis, we're going to get many different washers. And if we add up the volume of each one, that's going to be an approximation to the volume of the solid that we want to find. So let's sum all of these up, and this is what we get. And there we go. So now this is going to be an approximation to the volume of the solid that we want to find. Now, as we let the number of partitions n go to infinity, these rectangles will perfectly fill in the area between the two curves. You see, as we have it pictured here now, we have some area that's above the curve and some area that's missing right here. But as we choose more and more rectangles, they'll fill in perfectly the area between these two curves. And so if we take the limit as n goes to infinity, this quantity will equal the volume of the solid that we want to find. So this is equal to the volume that we want. Now notice that this looks a lot like the formula that we have up here. So when the limit as n goes to infinity, this piece right here turns into an integral. This part right here becomes our dx, like right up here. And this piece right here becomes our f of x, so we just replace each xi with an x. And we obtain the volume for our solid of revolution. So this piece turns into the integral from a to b. This piece right here turns into so all we did is remove the i's from the x's. And then we have our dx. And there you go. That's our volume for the solid of revolution. Just notice that the a and b, they're actually hidden in the summation up here, but they are there. And now let's take a look at a statement of our result and a few examples. So here's a statement of our result. If you're given two continuous non-negative functions, y1 and y2, with 0 less than or equal to y2 less than or equal to y1, so in other words the y2 curve is below the y1 curve on the interval AB, then the volume of the solid generated by revolving the region R, which is between the two curves for x between A and B, is given by this result down here. And this is what we had just derived. So it's going to be the integral from A to B of pi times y1 squared minus y2 of x squared dx. And that's what we have pictured over here. So if you take this region R right here between the two curves y1 and y2 for x between A and B, and you revolve it around the x-axis to sweep out a solid, the volume of that solid is given by this result right here. Now when you're using this formula, it's also helpful to think of the y1 as being the outer radius of a small washer, and y2 should be thought of as the inner radius of a small washer, and the dx should be thought of as the width. So if you think back to how we derived this formula here, you should think of drawing little rectangles like this, and then when this rectangle in here gets swept around the x-axis, it forms a washer. The outer radius of the washer, the distance from here down to the x-axis, that's your outer radius, and that's y1 of x. The inner radius right here, that is your y2 of x, for x being located right here between A and B. So that's how you should think of the y1, the y2, and the dx. Now if you were to take a region that looks something like this and rotate around the y-axis instead of the x-axis, then the formula that we have up here for x-axis rotation would look like this for y-axis rotation. Notice that we simply replace the y1 of x with an x1 of y, a y2 of x with an x2 of y, and then we integrate with respect to y instead of with respect to x. And we can see that from the graphic over here. You see we have this curve is x2 of y. Now that is considered to be our lower curve because with respect to the x-axis it is the lower curve, and the x1 of y is the upper curve with respect to the x-axis. And notice that we have this little rectangle drawn here representing a washer that would be formed as we rotate around the y-axis, and we have the points labeled here x1 of y, x2 of y, and so the outer radius of this washer is x1. So notice we should think of this x1 right here as being an outer radius, and the distance from here to here is x2, and so we should think of this x2 as being the inner radius of a washer. And so that's how our formula would change if we were to rotate around the y-axis. Now it's important to think of these values as being outer and inner radii, because as we'll see with some examples, when you rotate around axes other than the x or y axes, you'll have to change the x1, x2, and y1 and y2 functions. For example, if we were to rotate this region around the line x equals negative c, then if we look at our washer up here that is formed as we rotate around this line, we see that the outer radius of the washer would be the distance from our axis of rotation, or our line of rotation, out to this point. Now that distance is going to be c plus x1. You see this distance here, that distance is c, and then the distance out to this point would be x1. So this value here, the x1, would have to be changed to x1 of y plus c, and then we would have to square it. And the inner radius, that would change to c plus x2. You see this distance here is x2, so then this value here would change to x2 of y plus c, and then we would have to square it. So that's why it's important to think of these values as being inner and outer radii, because when we change the axis of rotation, we will have to modify these functions, as we'll see with some examples. And now let's take a look at a few examples. So for this example, we want to find the volume of the solid formed by revolving the region bounded between these two graphs about both the x-axis and then the y-axis. So the first thing you want to do when you're doing these types of problems is to get a good understanding of the graphs of your function and the region that you're revolving about the x or y-axis. So first of all, let's graph these two functions. Now down here we have the graphs. So here is the graph for the first one, which is g equals 2x. Now I'm going to call that one y1 equals 2x because of the notation that we had used previously. And the lower curve, that's the x squared function. Now this problem doesn't state any limits on the x values, like x is between 1 and 3. So we need to find where these two graphs intersect. So we're going to set them equal to each other, and then that'll determine our limits of integration. So if we set So setting those two functions equal to each other, we find that x can be 0 or 2. And so these are going to determine our limits of integration. So you see down here in this graph, we see that x equaling 0 is right here, and 2 is right here, and we see graphically it does look like that's where the two graphs cross. And so this is our region, the shaded region in here, R, that we want to rotate first of all around the x-axis. Now we have to determine which curve is the upper and the lower. Well, we already sort of did that by graphing these two functions. We see that 2x is above or larger than x squared for x between 0 and 2. So what we can do now is just directly apply this formula down here. This is our volume formula right here for rotation around the x-axis. So we can just directly apply this now, and we could write, now the a is going to be 0, the b is going to be 2. Now y1 is the upper curve, so that's 2x. Notice we need to write it in terms of x, because that's what we're going to integrate with respect to. And y2 is the lower curve, so that's going to be x squared squared. And there we go, that's what we need to evaluate. So this turns out to be and we can move the pi out in front of the integral, and we get, now the antiderivative of 4x squared, that's going to be antiderivative of x to the fourth, and now just putting 2 and 0 in here for x, we get 4 times 2 to the third is 8, and so 4 times 8 is 32 thirds. 4 times 8 is 32 over 3. 2 to the fifth, that's going to be 32 as well. And then when we put 0 in for x, of course we get back 0. And then just cross-multiplying or finding a common denominator, we get that this is equal to pi times 64 over 15. And there we go. That would be the volume of the solid that we would get by rotating this shaded region around the x-axis. Now let me show you another way to think of this problem, and this method comes in handy later on when we're looking at axes of rotation other than the x or y axes. So here's another way that I like to do these problems sometimes, and you might prefer this method as well. So here's another way to do this problem. If we want to rotate this region R about the x-axis, what I like to do is draw a line that's perpendicular to your axis of rotation down here. Now this line actually represents a thin rectangle that when rotated around the axis of revolution forms a washer. So if you want, you could add a little thickness to it to see that it's a rectangle, like that. And then I label points on the end of the rectangle. I'll call this point right here x, y1. And this point right here I will label as x, y2. Notice that I had to use a y1 and a y2 because the points lie directly above each other, so I have to distinguish between the y coordinates. So on the x-axis down here, this is x. y2 would be like right here on the y-axis, and y1 would be like right here on the y-axis. And now your volume, well, it's going to be pi times the outer radius squared. So now our outer radius is going to be the distance from the axis of rotation to the outermost point on the rectangle here. So that distance from here to here is being measured along the y-axis, and you see it's equal to y1. And then minus the inner radius squared, and that's this distance from here to here, and that's being measured along the y-axis, and that is y2. And then the thickness of this washer is, we'll call it dx, a small thickness to this washer right here. That's the distance, the thickness of the washer right here. And so that's what we're integrating with respect to. And then we have to think, what does the x vary from? Well, x can go from here, which is 0, out to 2, and those are our limits of integration. And once again, remember the way we find the 0 and the 2 for this particular problem is by setting x squared equal to 2x. And the solution to this is 2 and 0. So that's how we find those points. We did that previously. Now what we have to do is rewrite y1 and y2 in terms of x. And so now this is basically the same as it was before. Just notice that the point xy1 lies on this curve, which is y equals 2x. And so this point here is xy1, so this is actually y1 equals 2x. And so we just have to substitute the 2x in for y1. As for the y2, x comma y2 lies on the curve y equals x squared. And so putting these values into this equation, this becomes our y2 right here. So we see y2 is x squared, so we put the x squared in for the y2, and we get this. Which is exactly what we had before. And evaluating that as we did previously, you'll get which of course is the same answer that we had before. So it's really the same technique that we used previously. It's just that I like to draw a little rectangle like this and label the points on the end, and then use the coordinate points here and here to represent the outer and inner radius, and label them up here like this. So you'll see that comes in handy sometimes when we look at axes of rotation other than the x or the y-axis. Now for part B, where we want to rotate around the y-axis, we need to use this formula. So notice we have to integrate with respect to y, because we're going to go this way now. Okay, so we're rotating around the y-axis, so we have to integrate with respect to y. That's the way the disk and washer method work. So now we have to decide what are the upper curve and what's the lower curve. Well, the upper curve is now going to be this one. It switches because you see as we move this way along the x-axis, the larger curve now is actually this one. The one with the larger x values is this curve. So let's label this curve as x1 of y. Now what we have to do to solve for x1 in terms of y, we have to take the equation for this curve, which is y equals x squared, solve that for x in terms of y, and there we go. So the x1 is going to be the square root of y. So we will put this in place of the x1. Now the lower curve with respect to the x-axis is now going to be this one here, and we'll call that x2 of y. So now we need to take this equation, which was y equals 2x, and solve for x in terms of y. Well, if we divide the 2 to the other side, we get that x equals y over 2. And there we go. So x2 equals y over 2. So we will put this in place of the x2 now. And so what we get then is we get for our volume Now we need to determine our limits of integration C and D. Well, you see, for this region right here, the y varies from 0 on the y-axis, and the region continues all the way up to 4 on the y-axis. So our limits of integration are going to be 0 to 4 now instead of 0 to 2. And we just have to evaluate this integral now. Square root of y squared is y. Now the antiderivative of y, of course, is y squared over 2. Antiderivative of y squared is y cubed over 3, and then I divide that by 4, so we get, and then evaluate this from 0 to 4. So we put 4 in for y, 0 in for y, and subtract those two numbers. Now 0, of course, that's just going to be 0, so what we get here is and then simplifying this, we get our answer, pi times 8/3. And there we go. That would be the volume of this region, of the volume of the solid generated by revolving this region around the y-axis. Now let me show you another way to think of setting this up, similar to what I did previously. So here's another way to see how to do this problem. So we want to take this region, rotate around the y-axis. So what we do is we draw a thin rectangle represented by a straight line. If you want to, you can add a little width to it if you want. This line representing a thin rectangle is perpendicular to your axis of rotation. Now let's label the endpoints here. Let's call this one x1, y, and let's call this point right here x2, y. So notice x2 would be like right here on the x-axis, and x1 would be right here, and the y would be right there. So now our volume is going to be pi integral. Now we want to take the outer radius and square it. Now the outer radius is going to be the distance from here all the way out to here. Now this is being measured along the x-axis, so the distance is going to be x1. That's our outer radius squared. And then our inner radius is this distance. This is our inner radius, and that is x2. You see, that's distance. That is this distance along the x-axis right here. So that's going to be x2, and then we square it. And then we want to integrate with respect to y. You see, this rectangle here has a little thickness dy to it. Once again, if you want, you could draw a little thickness to that washer like that, and the distance, that width there, would be the dy. Notice it's measured along the y-axis. Now, as for our limits of integration, the y here on the y-axis can vary from 0 up to 4. And that 4 once again comes from the fact that if you solve these two equations, you set them equal and solve for x, you get x is 0 and 2. That's when you set, x squared equal to 2x and solve that, you get 0 and 2. And if you put 2 into either of these equations for x, you get back 4 on the y-axis. And if you put 0 in for x, you get back 0. And so the y varies from 0 to 4. Now what we need to do is rewrite x1 and x2 in terms of y. Now notice that x1y lies on this curve, which is y equals x squared. And if we solve this for x in terms of y, we get x equals the square root of y. Now that x is really x1, so there you go. So x1 is the square root of y, so we put that in here. This point over here, the x2, that lies on the curve y equals 2x. And solving this for x in terms of y, we get that x equals y over 2. And now this x is really x2, so x2 is y over 2. And so then this equation over here becomes pi integral 0 to 4. Which is exactly what we had before. And of course we get the same answer because we had the same integral right up here. And keep in mind this term right here we got by putting the 4 in for the y and then 0 in for y. So technically there's a minus 0 here, but I didn't write it because it's just 0. And so there you go. So that's another way of thinking how to do this problem. Just drawing a thin rectangle right here that is perpendicular to your axis of rotation, and then labeling points on the ends of the rectangle and thinking of the outer radius squared minus inner radius squared, and then rewriting terms with respect to the variable that you want to integrate with respect to. This technique comes in handy, as we'll see soon. And now let's take note of a special case of the washer method called the disk method. Now let's take note of this. In the formula for the volume of a solid of revolution, now this is for rotation around the x-axis, if the y2 is equal to 0 everywhere, so if this is equal to 0, that's what we're stating over here, then your solid has no central hole running through the middle of it, and your formula for the volume of a solid of revolution just becomes this, where this y right here is just the y1, redesignated as y, and the y2 is 0, so it goes away. And when this happens, we call this the disk method. So the disk method is just a special case of the washer method where the y2 is identically 0 everywhere. And if you have rotation around the y-axis, then your disk method just takes on this form. Remember, for rotation around the y-axis, you had x1 squared minus x2 squared. So if the x2 is identically 0, you end up with this formula, and that's a disk method for rotation around the y-axis. So let's take a look at this example. So let's find the volume of the solid formed by revolving the region bounded between the graph of y equals the square root of x, the x-axis, and the lines x equals 0 and x equals 9 about the x-axis and then about the y-axis. So the first thing you have to do for these problems is draw your region. Draw the graphs and then shade in the region that you're trying to rotate around whatever axis. So in this case, this is our region down here. You see this curve right here, that is the square root of x. The x-axis, of course, is right here. The equation for the x-axis, of course, is y equals 0. And then x is supposed to be between 0 and 9. So right here is 0, and right here is 9 on the x-axis. And so we want to take this region and rotate it around the x-axis and calculate that volume. So in this case, we see it's pretty easy. Our volume is just going to be that's our formula that we want to use. Notice this y represents an outer radius. If we were to draw a little rectangle like this, perpendicular to your axis of rotation, the outer radius, this distance from here to here, is y, and so y squared. The inner radius, you'll notice, is always 0. For example, that point right there is x comma 0, and so we just get the inner radius being 0 squared. This point right here is x comma y, and so the outer radius is y squared. That's exactly what we have right here. Now we need to change the y, rewrite y in terms of x so we can integrate with respect to x. Well, we already know y is the square root of x. Oh, and by the way, our limits of integration, x goes from 0 to 9. That's stated in the problem, so let's put that in there. There we go. And then just substitute in here what the y is. And there we go. We just have to solve that. And there you go. There's our answer, 81 over 2 times pi. So that would be the volume of the solid generated by revolving this region around the x-axis. Now let's take a look at part B. We want to rotate it around the y-axis now. Well, now that's actually not going to be the disk method. We're going to have to go back to the washer method for that one. So now if we want to rotate this region around the y-axis, once again, I like to just draw a little thin rectangle or just a straight line perpendicular to your axis of rotation. Let's label these points right here. For that point right there, the x coordinate is always 9, and it's sitting at some location y on the y-axis right there. This point right here I will call just a general x comma y. And so our volume is going to be, alright, now our outer radius, the distance from your axis of rotation to this curve, or in particular that point right there, is going to be 9, right? It's always 9. Okay, this is the curve x equals 9. That's what we have labeled right here. So the outer radius is 9 squared minus, now the inner radius is the distance from here to here, and so that's just x, right, for this general point, minus x squared dy. Y is the little thickness of this this rectangle right here that's measured along the y-axis. Now we have to rewrite x in terms of y. The 9 is fine as it sits here. We have to think about what are the limits of integration, okay? So what does the y vary from? Well, this y can go from 0 up to 3. Notice we get that 3 because if we put 9 into this equation right here, we get back 3, of course. So the y can go from 0 to 3. Now we have to write x in terms of y. Well, this point right here, x comma y, that lies on the curve y equals the square root of x. And so x equals y squared. So we just substitute y squared in for this x, and we get y to the 4th. Right? Y squared, x is equal to y squared, so y squared squared is y to the 4th. And then there we go. Now we just have to evaluate this. And simplifying this, 81 times 3 minus 3 to the 5th over 5. The 0 comes from when I put 0 in for the y's here and subtract. And we get 972 over 5. Okay, so that's our answer. 972 over 5 times pi. And you could, evaluate that on your calculator if you want a decimal answer. Now let's take a look at another example. Now in this example, we want to verify the volume formula for a sphere of radius r. The volume is given by 4/3 pi r cubed. That's the volume for a sphere of radius r. So we want to verify this formula by rotating the region bounded by this equation and the x-axis about the x-axis. Now if you graph this equation right here, y equals the square root r squared minus x squared, that is this curve right here. That's just a circle of radius r. Recall that if you take the equation for a circle of radius r, right, that's the equation for a circle of radius r, and you solve this for y, you get, now if we only take the positive square root here, then we get the upper half of a circle of radius r. Now right here is the x-axis, of course. That's the curve where y is equal to 0. Now our limits of integration, well, you notice that if we set y equal to 0 here and solve for x, the x can be plus or minus r. So there's negative r, and out here is positive r. Once again, notice that if we set this equation, set that equal to 0, well, of course that's going to be 0 when x is r. R squared minus r squared gives you 0. And when x is negative r as well, r squared minus negative r squared, that's going to be 0 also. So that's how we get negative r here. So now we want to rotate this region around the x-axis. So now, once again, if you like, you can draw a little rectangle perpendicular to your axis of rotation, a thin rectangle like that. Label that point right there. That would be x comma y. This point right here would be x comma 0, right? The y is always 0 for this point as it slides along here. And so our volume formula is going to be, so the outer radius squared, well, the outer radius is the distance from here to here, and that's the y coordinate here, so that's y squared, minus the inner radius squared. Well, the inner radius is always 0, right? This is basically just the disk method here. We don't have an inner radius, so 0 squared, dx, right? We're integrating with respect to x because we're rotating around the x-axis, and also you can think that this washer here has a thin width to it, dx. Now, as far as our limits of integration go, we could integrate from negative r to r, but it's a little easier in this case if we integrate from 0 to r and then just multiply this by 2. So we're going to do that. You see, so we're only going to take this region right here, this half, and rotate it, and then just multiply our answer by 2. It's just a little easier to do that because I have a 0 in the lower limit of integration, then makes it a little easier when we evaluate our integral that way. So we're only taking this portion. You would still get the same answer if you went from negative r to r and left out the 2, no problem. Now we have to write y in terms of x. Well, of course, right here is y in terms of x. This point right here, x comma y, lies on this curve. And so, just putting x in for x, y in for y, of course, y is equal to the square root. There we go, left out the 0, and now we just have to evaluate this, and we will get 4/3 pi r cubed. Square root squared, of course, the square root goes away. Be careful when you're integrating with respect to x, so you need to treat this r squared as a constant, like the number 5. Antiderivative of 5 is 5x. Don't integrate this with respect to r, thinking of this as being r cubed over 3. The r is a constant. So now we just plug r in for x, 0 in for x, subtract, and we get our answer. And there we go, 2 pi times r cubed minus 1/3 r cubed. And so what is in here is going to be 2/3 r cubed, and so we get, and 2 times 2 gives us our answer, 4/3 pi r cubed. And there you go, we have just verified the volume formula for a sphere of radius r. And also, once again, just notice that when I plugged the 0 in here for the x, I got minus 0 here, so I just left that out. Now let's take a look at solids of revolution about other axes, meaning axes other than just the x and y axis. So let's take a look at this example. So here we would like to set up the integrals representing the volumes of the solids formed by revolving the region bounded between these two graphs about these lines. So first of all, about the line y equals -1, then y equals 5, x equals -1, and x equals 3. Now we're just going to set up these integrals. They'll be pretty easy to evaluate if you wanted to do that. So the first thing to do, of course, is graph your curves and get a good picture of the region that you're rotating. So down here we have the graph of our two functions. That lower, the graph right there, the lower curve, that's y equals x squared. And the straight line right here, of course, that is y equals 2x. Now for the first one, part A, we want to rotate around the line y equals -1. So right there is -1 on the y-axis, and we want to rotate around this line. So we want to rotate the region around here instead of just the x-axis, say. So this is our region R. Now this is where it comes in handy to draw a little rectangle, a thin rectangle perpendicular to your axis of rotation. So let me draw just a thin little rectangle like this, or you could just do a straight line perpendicular to your axis of rotation, and let's label the points here and here. So those are going to then give us our outer and inner radii. So let's call this point right here, I'll call that x comma y1. I have to distinguish between the y coordinates because it's a vertical rectangle. And let's call this point x comma y2. The value x, of course, is right here on the x-axis, so that's x. Y2 would be over here, and y1 would be right about there on the y-axis. Now we just follow our standard formula. Outer radius squared minus inner radius squared, and we integrate with respect to the axis of rotation. So for part A, our volume. Okay, so now our outer radius, and we have to square it. Now, our outer radius is the distance from our axis of rotation up to this point right here. So this distance. So you see that distance is being measured along the y-axis. So it's going to be y1 plus 1. You see that? This distance right here, that distance is 1. And this distance is y1. See, y1 only measures the distance from here, the x-axis, up to that point. So it's going to be y1 plus 1. That's your outer radius, and then we have to square it. Now your inner radius is going to be the same thing, except instead of y1 we have y2. So the distance from your axis of rotation up to your inner radius, or your lower curve here, is going to be y2 plus 1 squared. And then we're integrating with respect to x, because the thickness of this little rectangle is a dx. See, it's being measured with respect to the x-axis. Now our limits of integration, we didn't do those. They're again going to go from 0 to 2. And once again, we get those limits of integration by setting the way we have this region drawn. You see, we want to find the intersecting points of the two curves. So once again, you set x squared equal to 2x. And of course, that tells you that x is 0 and 2, just solving this equation for x. You know, you can take the, write this as x squared minus 2x equals 0, factor out the x, and you'll get those two numbers, of course. Now what we have to do is replace the y1, or write y1 in terms of x and y2 in terms of x. Well, y1, x comma y1 lies on this curve right here. So if we put x in for x, y1 in for y, you know, we get y1 equals 2x. There you go. We just have to substitute that in for the y1. The y2, x comma y2 sits on the curve y equals x squared, so put y2 in for y, x in for x, and you get y2 equals x squared, of course, so put x squared in place of y2. And then we square this, and we integrate with respect to x, dx. And there we go. That's our answer to part A. And you could easily evaluate this if you wanted. You know, you could FOIL out each of these terms. You would get a fourth degree polynomial in here that you could easily anti-differentiate and evaluate from 0 to 2 to get your answer. Now let's look at part B. Now for part B, we want to rotate around the line y equals 5. So let's put y equals 5, that line on the graph here. So this is our line y equals 5 right here. And that is 5 right there on the y-axis. So now the same formula as before. Our volume is going to be pi times the integral of the outer radius squared minus the inner radius squared. So now we have to find out what is our outer radius and square it, and our inner radius and square it. Now our outer radius is going to be the distance from here, our axis of rotation, all the way down to that point on our lower curve. Now that point is x comma y2. So this distance from here to here is this distance over here. Label it like this. So we want to find that distance. Well, that's being measured along the y-axis, and you see it's going to be 5 minus y2, right? The distance from here to here is 5, and I have to take away this distance, which is y2. That'll give us our outer radius, and so we have 5 minus y2, and we square it. Now our inner radius is going to be this distance. That's our inner radius now, the distance from here to here. And so you can see that that is going to be 5 minus y1, right? The distance from here to here is y1. Distance from here to here is 5. So 5 minus y1 squared. dx, and x varies from 0 to 2. And now we just need to rewrite y1 and y2 in terms of x, and we'll have our answer. Well, x comma y2, once again, that lies on the curve y equals x squared, so y2 equals x squared. y1, that x comma y1 lies on the curve y equals 2x, and so y1 equals 2x. And there you go. You could FOIL out each of these terms in here. You would end up with a fourth degree polynomial that you could easily evaluate to get your answer. So that's our answer to part B. Now let's do parts, we should have parts C and D right here, not B and B. Now part C, we want to rotate around the line x equals -1. So let's set that up now. So now we have to basically change everything around. We're going to rotate around the line x equals -1 first. So -1 on the x-axis is right there. So we want to rotate around this line. Like that. Now we have to orient a little rectangle like this. Okay, and now we're going to think of rotating this around this line right here. Let's label these 2 points on the ends of the rectangle. That point right there, I'm going to call x1 comma y. And that point right there, I'm going to call x2 comma y. And you see y is right there on the y-axis. x1 is right here. And x2 is right here. Now we just have to do the same thing that we've done before. Volume is going to be integral pi times outer radius squared minus inner radius squared. Okay, the outer radius is now the distance from here to here. Well, that's being measured along the x-axis, so you see it's going to be this distance is 1 plus x1. See that? x1 is the distance from here to here, and the distance from our axis of rotation to the origin is 1, 1 plus x1, minus the inner radius. All right, now that's going to be 1 plus x2. dy, because the thickness of this little rectangle right here is a dy, right? Thickness is being measured with respect to the y-axis. Now, what does the y vary from? Well, if we plug 2 and 0 into either of these equations up here, you see you get back 0 and 4. So the y can vary from 0 up to 4. And now we just need to rewrite x1 and x2 in terms of y's, so we can integrate with respect to y. Well, let's see, the x1 comma y, that lies on this curve y equals x squared. So we have to solve for x in terms of y. So from here we get that x equals the square root of y. We only want the positive, not the negative one here, because of the because this curve lies in the region where x and y are both positive. And putting x1 in for x, y in for y, we get that x1 equals the square root of y. So square root of y goes right here. The x2, that lies on the curve y equals 2x, or x equals y over 2. So putting x2 comma y in here, I get x2 equals y over 2. And so this is going to be 1 plus y over 2 squared dy. Oh, and I forgot my square right here. That's a square right there. And there we go. You can FOIL each of these out, and you'll be able to easily integrate it. Now let's take a look at part D right here about the line x equals 3. So let's change this up now. Now right here is the line x equals 3. And we'll keep the same orientation for our little rectangle down here. All the curves are the same, of course. And so our volume, outer radius squared. Now the outer radius is going to be the distance from here to here now. So this distance, that's the distance, that's this distance right here. That's going to be 3, right? This is, by the way, that is 3 right there on the x-axis. 3 minus x2 squared minus, now the inner radius is the distance from here to here, so that is this distance. So that's going to be 3 minus x1 squared dy. And y still varies from 0 to 4. And now we just need to rewrite x2 and x1 in terms of y, which we did previously. Well, the x2y, that lies on the curve y equals 2x, or x equals y over 2. So putting x2 in for x, y in for y, this is y over 2 squared. x1, x1 comma y lies on the curve y equals x squared, or x equals the square root of y. Putting x1 in for x, y in for y, we get x1 equals the square root of y. dy. And there you go. That's our answer for part D over here. You could easily FOIL this out again and integrate from 0 to 4, and you'll get your answer. And that concludes our discussion about the washer and disk methods.